For over 6 decades, steam catapults formed the backbone of naval aviation for the United States Navy. From the Forrestal class supercarriers to the Enterprise class, through the entire 10-ship Nimitz class, steam catapults powered every fixed-wing aircraft launch from a supercarrier. The mechanism was loud, maintenance-intensive, and demanding, but it worked. Millions of successful launches proved its utility in Cold War standoffs and combat operations worldwide. When the US Navy designed the new Gerald R Ford class supercarriers, engineers decided to break from this legacy. They replaced steam catapults with an all-electric catapult mechanism known as the Electromagnetic Aircraft Launch System, or EMALS. This transition marked the largest shift in carrier technology since the introduction of the angled flight stick. The United States was not alone in recognizing the potential benefits of electromagnetic catapults. China followed a similar path with its third carrier, the Type 003 Fujian. The Chinese People's Liberation Army Navy chose to skip steam technology entirely, moving straight from ski jump ramps on its earlier carriers to electromagnetic catapults on the Fujian. Yet, as the USS Gerald R Ford entered service in the US Navy, early technical challenges and lack of reliability raised critical questions within the military establishment. Some commentators and officials even suggested that future ships of the Ford class should abandon EMALS and return to steam catapults. To evaluate whether that argument holds merit, we must look closely at how these two technologies function, where EMALS succeeds and where it creates operational vulnerabilities, and what a return to steam would actually mean for the future of American carriers. To understand the debate, it helps to examine how EMALS operates in simple terms. A traditional steam catapult relies on high-pressure steam tapped directly from the ship's nuclear reactors. The steam fills a long trench underneath the flight stick. When released, the steam rapidly pushes a heavy piston forward along the track, pulling the aircraft attached to the shuttle down the deck until it reaches flight speed. EMALS replaces the high-pressure steam, the pipes, and mechanical valves with electricity and magnetic forces. Beneath the flight stick lies a linear induction motor. When electric current flows through stationary coils along the track, it creates a moving magnetic wave. This magnetic wave pulls a motor carriage attached to the landing gear of the aircraft along the track at high speed. To deliver the massive burst of electrical energy needed for a launch, up to 120 megajoules in 2 seconds, EMALS draws power from the ship's generators and stores it in flywheels called energy storage rotors. During a launch, these flywheels release their stored energy into solid-state power converters, which feed the exact amounts of electrical currents into the motor to accelerate the jet smoothly to its required takeoff speed. The advantages of EMALS over steam catapults are substantial. The primary benefit is the ability to finely control acceleration across a broad weight spectrum. A steam catapult delivers a sudden burst of force when the steam valve opens. This initial power stroke is difficult to control precisely. As a result, steam catapults apply harsh physical forces to the aircraft. Furthermore, steam catapults struggle to adjust force downward for light aircraft without risking a failed launch when a catapult fails to generate enough speed for takeoff. EMALS solved this problem using digital power management. Operators can set the precise thrust tailored to the exact weight and airspeed requirements of a specific aircraft. This allows a Ford-class carrier to safely launch lightweight, unmanned aerial vehicles weighing just a few tons, such as future autonomous reconnaissance drones, without damaging their airframes. At the same time, EMALS can adjust upward to launch heavy strike fighters like the F/A-18E Super Hornet or F-35C Lightning II, carrying full internal fuel and maximum weapons loads up to 45 tons. This precise control over acceleration directly improves aircraft longevity. Repeated steam catapult launches create structural fatigue on airframes and landing gear. By delivering a smoother acceleration that eliminates the initial violent shock of steam, EMALS reduces stress on the aircraft. Over thousands of operational launches throughout a jet's service life, the smoother stroke preserves airframe integrity, reduces maintenance hours, and extends the operational lifespan of expensive carrier-based aircraft. Another major operational advantage is the potential for a higher sortie generation rate. Sortie generation measures how many combat aircraft a carrier can launch, recover, arm, and relaunch over a given period. EMALS recharges its energy storage flywheels in roughly 45 seconds, which is faster than the time required for a steam catapult to refill its tanks with high-pressure steam. Combined with the advanced arresting gear installed on Ford-class carriers, EMALS enables faster launch cycles. In high-intensity combat scenarios, the ability to launch more combat sorties per day gives a supercarrier higher overall firepower. Critics of EMALS frequently cite the severe reliability issues encountered during the early testing and deployment phase of the USS Gerald R Ford. During sea trials and early deployment, the system suffered frequent failures, falling far short of the Navy's goal of over 4,000 main cycles between operational failures. Catapult's breakdowns frequently halted flight operations, leading to public criticism from senior military leadership and politicians. However, recent operational experience demonstrates that these early reliability problems have been largely resolved. Software updates, hardware refinements, and improved maintenance have steadily increased reliability. During recent deployments in the Atlantic and Mediterranean, the USS Gerald R Ford completed thousands of consecutive launches without major system outages. The maturity of EMALS on the lead ship suggests that future reliability problems on follow-on vessels like the USS John F. Kennedy, USS Enterprise, and the Doris Miller will be substantially mitigated from day one. Despite these gains, arguments for returning to steam catapults persist among defense analysts and naval officers. The most compelling arguments rest on established training pipelines, operational standardization, and fleet-wide technical expertise. The US Navy operated the C-13 series of steam catapults for decades across the entire Nimitz class. Tens of thousands of sailors, technicians, engineers, and officers were trained under standardized procedure to operate, inspect, and repair steam systems. Supply chains for steam catapult components were fully established worldwide, with spare parts stockpiled across naval depots and supply ships. Transitioning back to steam would leverage a massive reservoir of operational knowledge and existing logistical infrastructure that EMALS is still building from scratch. A serious engineering criticism of EMALS involves system isolation and fault tolerance. On a Nimitz-class carrier, each of the 4 C-13 steam catapults operates as an essentially independent mechanical system. If catapult number 1 suffers a mechanical failure or requires routine maintenance, catapults 2, 3, and 4 can continue launching aircraft without interruption. Steam lines can be isolated via physical valves, allowing technicians to work safely on one catapult while flight operations continue on the others. The architecture of EMALS on the Ford class is fundamentally different. To save space and weight, engineers grouped the electrical power conversion and energy storage subsystems across catapult pairs. Catapults 1 and Catapults 2 share energy storage rotors and power conversion units, while Catapults 3 and Catapults 4 share a separate power block. Consequently, a single electrical fault or power converter failure in one shared subsystem can simultaneously disable two catapults. Furthermore, the high-voltage design makes it difficult to isolate one catapult for safe maintenance, while high-voltage current is actively flowing through the adjacent system during flight operations. In a combat situation, losing two catapults to a single electrical fault significantly degrades the carrier's combat capability. Finally, steam catapults possess an unmatched record of battle-tested reliability over long histories. The C-13 steam catapults, including those used on the Kitty Hawk and the Enterprise, proved its durability in high-intensity combat situations, including conflicts in Vietnam, the Persian Gulf, and modern contingency operations worldwide. It operates without complex microelectronics, digital control, or high-voltage electronics that could be vulnerable to electrical surges, overheating, or electromagnetic interference in hostile environments. Steam is mechanically complex, but the physical conditions for its failure are well understood by the sailors on board. When weighing these competing factors, the question remains: should future ships of the Gerald R Ford class return to steam catapults and forego EMALS? The short answer is no, despite the benefits of steam. Reverting to steam catapults on future Ford-class carriers would be costly and a move backward for the United States Navy. Redesigning the Ford-class hull to reintroduce steam catapults would require massive structural and engineering overhauls. The ship was engineered from the keel up around an integrated propulsion and power distribution system. Restoring steam catapults would require running heavy steam piping throughout the ship, reallocating compartment space, and modifying the nuclear reactor steam plant. The engineering cost and construction delays of such a redesign would far outweigh any immediate operational benefit. Furthermore, EMALS is vital for the future carrier airwing of the United States Navy. As the Navy integrates heavier strike platforms alongside lightweight, uncrewed aircraft like the MQ-25 Stingray aerial refueler, the granular acceleration control offered by EMALS becomes a necessity. Steam catapults simply lack the operational flexibility required to launch the next generation of carrier aircraft safely. While the lack of isolation between individual EMALS catapults on the Gerald R Ford class remains a key design deficiency, the solution is targeted refinements, not systemic retreat. Future Ford-class carriers can incorporate improved electrical isolation and redesigned power distribution to ensure single-point failures do not degrade multiple launch tracks simultaneously. EMALS represents the future of naval aviation. With its initial technical hurdles largely overcome, the US Navy must focus on perfecting electromagnetic launch technology rather than returning to the past into steam catapults, undoing the innovation it has achieved.